So, hello everyone, welcome back to the course on architectural design of ICs. So, we have seen different CORDIC architecture. So, we can implement various kind of functions or operations we can do. We can run that CORDIC in a different mode, 6 different mode we can run. Using 6 different mode, various kind of that means this arithmetic operation we can do or we can perform. It is not only limited to that, based on that particular function calculated, again we can calculate some more of the functions that we have already seen. We have seen the that means this parallel architecture or this serial architecture that we have seen, and what I said that there are, that means this is also one very rich field of research. Okay. So, people have find out as this CORDIC has a vast application area. So, that is why people have tried so much to get more high performance architecture for this CORDIC algorithm. Okay. So, like here what we are doing, what makes it that means what is the critical point if we see at the very first, and then from that point if we try to analyze that how we can improve the corresponding performance of the CORDIC algorithm. So, I think that will be step by step research methods. Okay. So, the very first what we have to do, the important factors of CORDIC we have to concentrate or we have to notice. Okay. So, the important factors which are basically related to CORDIC, that is, I need addition subtraction operation, which is if we choose the number of bits are more. So, at that time the corresponding delay will be more. Then there is another thing which is that scaling factor. So, scaling factor is basically that is 0.6073, that is in the fractional domain. Okay. And then again the thing is that the sequential execution, that means the CORDIC algorithm is basically has been done on based on what, that x I plus 1 equals to x I minus d I into 2 to the power minus I of y I, right. So, that means the I plus 1 rotation that is dependent on x I plus 2 that is dependent on I plus 1. So, that means each of these cycle is basically dependent on the previous one. So, can I use, so that means as this algorithm itself it is sequential. So, at that time how can I make it faster? So, that means if it is sequential, that means it will take time. Suppose like if I take one example of that, suppose if I have to walk a road, okay. If one step by one step if I am going, then how much time I will take to cover up that road if I take 2 steps at a time or 3 steps at a time or 4 steps at a time. So, at that time the time to cover that particular path that will be lesser. So, here also the same thing, that means to compute the whole task or to perform the whole task, if one step by one step if I do, so at that time it requires, if I run it for 10th iteration, so 10 clock cycle I require. But if I that means do 2 iteration at a time or 3 iteration at a time or 4 iteration at a time, if we can perform, so at that time the time requirement that will be lesser. Okay. So, that means what we can do in this parallel, what we are doing, that means the input and output they are basically dependent on, that means whenever the inputs are available at that time whatever is the delay and how many levels of that particular data subtractor is there, depend after that much of time I can get my output. So, instead of doing that, what we are doing, the sequential one is basically taking less time. So, if we can make radix 2 or 3, that means some kind of mixed architecture, that means few of the steps if we can do sequentially and few of the steps if we can do parallelly. So, at that time I can get the area benefit as well as the time benefit both the way. So, that kind of architecture also we can think of. So, that is why people have developed, there are, if you find in the literature, definitely you will find the literature, that means this radix 4 CORDIC algorithm, then radix 8 algorithm, that means increasing the radix, or that means increasing the step per iteration, I can reduce the time, though the complexity wise it will be more. Okay. So, again what I said, the last point here is that sequential execution of the algorithm itself. So, can I make it parallel kind of things? So, one of the, that means literature is there, or one of the it is not that the only this particular architecture is there. So, this is just one example of that. If I have to think that if I want to make this architecture, or if I want to get the time, that means to the computation time will be lesser. So, at that time I have to make that algorithm parallel by itself. So, how can I make that? If I can make that, then what will be the change in the architecture? So, that we will see, and if I make the change, so at that time what is the area as well as what is the, that means delay wise how many or what is the advantage I am getting, that we will see. This is just only for an example. This is not that only this architecture is available on the market. There are several architectures available on the market for CORDIC algorithm. This is just to show you the example how you can proceed in this particular direction. Okay. So, this research topic about this is little bit, that means I am giving you just one overview of doing research in this particular area or the CORDIC architecture. So, there are like this redundant CORDIC architecture, then this error analysis of CORDIC, then application of CORDIC architecture, then this CORDIC algorithm with non-constant scaling factor, and then parallel CORDIC architecture. Okay. So, that means what? In CORDIC what we do? We basically gather some of the errors. Whenever we are doing iterative, if we gather in one stage, if we gather some of the errors, so in how many iteration I will continue, so that much error I will accumulate. Okay. So, that means error free CORDIC also architecture is also available. Okay. And all this because of vast application of the CORDIC architecture. So, now what we are trying to focus on, that is the parallel CORDIC architecture. Okay. So, what is the bottleneck of CORDIC rotation? This is the basic equation of conventional CORDIC, that is xi plus 1, that is dependent on xi. This is this sigma here means this sine of z, and then 2 to the power I a of yi. Okay. So, the conventional, that means the corresponding bottleneck is that the sequential determination of sigma I based on this z I, because depending on this sign we can compute each of this iteration, whether that will be plus or that will be minus. In this case also, whether that will be plus or in this minus, it depends on the sign of this. So, this particular thing, sign of calculation of this sign of this sigma I based on this z I, that makes the CORDIC algorithm sequential. Okay. So, that means as this path is running one by one, so that means this is basically taking the time for that. That is why we are not making this CORDIC as a parallel one. So, that is why what we can do, this is a new method. So, what we are trying to do, we are basically taking each bit of input angle to determine this sigma I. Means what? Whatever input angle we are giving, we are considering each of this bit position, whatever is the bit values of this input angle, based on that we are basically trying to determine this sigma I, because the elementary angle that are pre-computed, right. So, pre-computed means if that is suppose 30 degree, right. So, 30 degree means that is lesser than, if I consider bit wise, that is lesser than the 45 degree. So, obviously, if that means if it is below 45 degree, so obviously the sign will be -1. So, the input angle is given to me and the elementary angle is also known to me. So, on that, considering those facts, can I from the beginning can I calculate each of these sigma? Can I do that? So, I can do, or based on that, considering that particular fact, this parallel CORDIC architecture has been evolved. Okay. So, what it does, it basically in the first m-1 iteration, it basically follows this sequential whatever is the conventional method, it follows for the first m-1 iteration. But for the other iteration, if b is the number of bits, for the other iteration it basically performs parallel operation. Okay. So, how means what? So, this is the elementary angles. Okay. So, whenever we are considering this, that for 2 to the power -3, 2 to the power -4, 2 to the power -5, 2 to the power -6, there mostly, that means only 1 or 2 position of this is 1 and rest of the positions are like mostly filled with 0. We have to consider this in the binary. To represent this corresponding that the values of for 45 degree, tan inverse of this 45 degree, that means which is in the radian. So, those value can be represented in terms of this. So, in the actually if you just follow that particular you have to that means connect with the table. So, in the table you will notice that for the z calculation it is basically the theta, but it is recorded in the radian mode. Okay. So, those values now you can basically recorded as this, but whenever it will come to, that means this -2 to the power 3, -2 to the power 4, that means for the lower values of this, the number of ones in this particular bit, that will be lower. Okay. Here it will be mostly dominated by the number of zeros. So, that means for the what it said, for the first where there is 0 combination of zeros and 1 are, that means they are almost like similar, or there still it is, that means it is not that only one factor is dominating. So, at that time we can follow this sequential approach, but where from this mostly 0 will dominate over 1. So, at that time we will use this parallel architecture. Okay. So, based on that there are two that means technique, which is this micro rotation to angle recording, and then there is binary to bipolar recording. So, how you can do? Suppose this 2 to the power -1. So, at that time it will be written as tan inverse of 2 to the power -1 plus tan inverse of 2 to the power -5 plus tan inverse of -2 to the power 8 plus error of this, which is nothing but this 2 to the power -9. Okay. And but in binary to bipolar recording, how it will be recorded? This polarity will be different. That means for each of this, 1 will be recorded as 1, but 0 will be recorded as 1 bar. Okay. So, this you can see for 0.101, this will be recorded as this 1 bar 1. Okay. So, 1 for this, then 0 for this, 1 for this, something like this we have to do. So, that means what? This there will be having 2 phase. What I said, according to the algorithm there will be 2 phase. When one phase it has to pass for m-1 iteration, it has to pass sequential. For other iteration, which is if I consider b number of iteration. So, b minus m minus 1, b minus m plus 1 number of iteration, that will be considered in parallel. Okay. So, in phase 2 we have to do that. Okay. So, considering this, here you actually some extra elements or extra, that means things you have to be, or extra circuitry you have to modify or introduce in this particular circuit. Okay. So, this is the algorithm for this micro angle rotation technique. Okay. And actually this is the results what we are getting. That means for different of number of bit, where m means the first 11 iteration are sequential, rest 21 iteration they are run in parallel. Okay. So, if I run that in parallel, so at that time the corresponding values of this, what is the values of signal, that means this sign, that is calculated based on the algorithm or this flow chart which we have already mentioned over here. Okay. So, this is the architecture for that, that means based on that particular algorithm. Now, we are getting this architecture, this is the architecture 1, and here you see how we are calculating the sign, that means the that sign that has been calculated considering these 3 things, that is S1, S5 and S2, S8, based on what, that 2 to, if 2 to the power 1, then tan inverse of 2 to the power minus 1, tan inverse of 2 to the power minus 5, tan inverse of 2 to the power 8, these 3 has been considered together, and to find out the corresponding sign for that. And each of this case, now considering this, in each of this sign has been computed from the beginning. That means, whenever for the lower part the sign has been calculated from the beginning, where I am basically doing the parallel architecture, or I am running that in the parallel mode. Okay. So, this micro rotation of this is being realized using this carry save adder. So, carry save adder we have already seen in the adder chapter. So, carry save adder basically that is very much useful for that means this delay wise compression. So, it takes lesser time than the normal one, normal ripple carry one. Okay. So, that we use to reduce the, to calculate this micro rotational angle, that means to find out this sign based on this parallel that means algorithm. Okay. So, whenever we evaluate this particular structure, so this Z path means whenever we evaluate this, so at that time this corresponding delay is this log 3 by 2 m plus 1 into TFA, that means TFA is the delay for one full adder cell. So, m is what? M is the number of iteration, initial iteration where I am running the CORDIC in the parallel mode. Okay. But area wise it is B minus m plus 1 into m minus 1 into A of FA. That means, A of FA is the area of one full adder cell. Okay. So, that means delay wise it is taking this, and area wise it is taking this much of that area. So, this much of area means, so for m minus 1 stage is there, and then again B minus of m plus 1 stage is there. So, both are basically considered together, and then that is multiplied with 1 unit of full adder area to get the total area. But delay wise it is more or less, because I am considering this running the, that means this iteration, that means CORDIC only for the m number of iteration in a sequential mode. Okay. So, that is why this delay is reduced over here. Okay. So, considering B different B and M. So, what I said, B is the number of stage I will consider, among which M is the number where how many numbers the CORDIC will run for sequential, rest of the case it will run in parallel mode. So, that means 5 is the case where it is running for sequential, 7 is the, that means rest 11 modes they are running in parallel. Okay. So, the carry save addition levels it is required, that is 3, and then the delay in unit of that is also 3, and then this carry save adder, number of carry save adder required, that is 4. So, total area will be 48. Okay. So, why 48? Considering this fact, if you just calculate, then you will get this. Okay. So, considering different values of B and M, now we will get different in delays and different in terms of area. Okay. And if we consider that previously introduced CORDIC rotation, that means first CORDIC architectures. So, this is one of this that means architecture which is being published in 1997 in IEEE transaction on computers, where they have followed this first m minus iterations are in sequential. Okay. So, considering this fact, this is getting the delay amount is of this log 2 base B into B by 3 plus 4 B by 3 into TFA, whereas this area is 4 B square plus log 2 base B into B square divided by 3 into AFA. So, this is one of the, that means architecture which has been proposed in 1997. So, in 1998 another architecture has been proposed, which basically based on this double hardware to perform clockwise and counterclockwise rotation. That means, here what we are doing, that means in the positive domain, that means suppose we are doing positive. So, that means we are running that as a counterclockwise. Whenever we are coming down in the negative, so that means we are running that in count, that means clockwise. So, that clockwise rotation and counterclockwise rotation from the beginning using double hardware, from the beginning if we can try to pre-compute, and then if you store this information, and then again if I have to use that to reduce the time. So, we can, that means here this particular architecture is mainly to reduce the time requirement or the computation time of the algorithm, that means CORDIC algorithm. To reduce that, focusing on that particular aspect, this particular architecture has been developed. So, here what is that? That means as we are introducing or we are using that double hardware to perform this clockwise as well as this counterclockwise rotation. So, that means area cost will be higher, because we are doing parallel things in counterclockwise rotation checking as well as counterclockwise rotation checking. That means, we are computing, basically computing the sign from the beginning by considering both clockwise rotation as well as counterclockwise rotation. So, here you see the delay wise it is much more lesser, that means that is why this B by 2 into 5 into TFA, whereas that area wise it is 18 B square plus 6 B into FA. So, area wise it is much more costly. So, then again in 2000 again one work has been produced, where this complicated logic circuit to generate the fast m minus 1 rotation direction. So, that means here all the things from the beginning, considering the input rotation, that means input angle given, based on that we are trying to pre-compute the sign values, and then we are trying to use the in the iteration mode. So, here this the delay is B plus this and the area is this. Okay. Then again in 2002 this ROM based, that means the corresponding iteration, that means the sign that has been also been stored in the ROM, and then again it is used for this each of the iteration, and then this is the corresponding that delay for this is the area for this. Okay. And this parallel CORDIC architecture, whatever we have seen just now based on this MAR algorithm, which is this micro architecture, that means angle rotation technique. If we see the delay and the corresponding area cost is this much. Okay. So, if we just compare these four work, so if you see different, considering the different size of B, if you are getting the proposed one, means this is the parallel CORDIC one. Okay. So, parallel CORDIC is basically having lesser delay in all this consideration. Okay. And area wise consideration also, you can see in some case it is getting higher. The yellow one is the lower one. Yellow one is the which one? Yellow is the one which is the this one. Okay. So, area wise it is having the savings. Okay. So, area wise it is having the savings, means that is why it is lesser than the parallel CORDIC one. Okay. And this double hardware based, area wise it is having the maximum one. Okay. So, this 1980 work, this work has double hardware for clockwise and counterclockwise rotation. So, this is having more area than among all these architecture. But if you just see, that, but delay wise it is not that much, whereas the this work area wise it is saved, but time wise it is more on each of these case. Okay. So, then this, what is the application area of this? Application area of this is for ROM based implementation of sine and cosine generation. So, sine and cosine generation where we require, suppose you want to implement this frequency synthesizer, this digital frequency synthesizer, or suppose you are that means you have to develop one this transmitter or receiver. So, for the IF frequency mixing you need that digital frequency synthesizer, which will be of different frequency, that means sin theta and cos theta. So, that sin value and cos value you have to generate. So, at that time you can use CORDIC to generate that sin and cos. Okay. So, that means, and whenever you are putting that thing, or you are using that for those type of application. So, at that time computation time will be, obviously it requires lesser time, because in wireless communication or the transmitter or receiver specification, this your hand of time or the time computation for doing the whole transceiver operation, that is a very much important factor, which is basically related to hand off signal in your cell phone or this wireless signal processing blocks. Okay. So, on that case computation time it is required, that is very much lesser. That type of application require this kind of architecture to be developed. So, this is one of the particular aspects or one of the particular example which I am showing you to show the research direction for this particular area. This is not the fact that, again I am saying that this is not the fact that this is the only architecture which is available, and this is there are now in 2000, I think we are in 2018. So, there are several architecture which people have introduced or people have already proposed or invented. So, if you are interested in this direction research or your work on this particular direction, so please go through those or please let me know. So, thank you for this. This is the end of this CORDIC chapter. In the next we will try to see this first Fourier transform architecture, the VLSI architecture of first Fourier transform, and then again we will try to see that different kind of this timing strategies, what are the hazards, and then that means what are the glitches which occurs in the circuits, in digital circuits, and then again if time permits, then obviously we will try to show you this what is the meaning of static timing analysis, what is the need of, that means just the basic of static timing analysis. But mostly if I do not cover in the lecture those things, if you ask, then obviously surely I will that means provide you the documentation which through the via the discussion forum. You just request me, obviously I will try to share those. So, thank you for today's class. Again we will meet on the next class.